Section 10.5 Further applications of the ideal gas equation. The ideal gas equation can be used to determine many relationships involving the physical properties of gases. In this section, we use it to first define the relationship between the density of a gas and its molar mass, and then to calculate the volumes of gases formed or consumed in chemical reactions. Gas densities and molar mass. The ideal gas equation allows us to calculate gas density from the molar mass, pressure, and temperature of the gas. Recall that density is the units of mass per unit of volume. We can rearrange the gas equation to obtain similar units, moles per unit volume. So N over V equals P over RT. If we multiply both sides of this equation by the molar mass, which is the number of grams in 1 mole of the substance, we get number of moles times the molar mass over its volume equals the pressure times the molar mass over RT. The product of the quantities N over V and M equals the density in grams per liter as seen from their units. Moles over liter times grams per mole equals grams per liter. Thus, the density of a gas is given by the expression on the right in equation 10.9. The density equals pressure times the molar mass divided by RT. From equation 10.10, we see that the density of a gas depends on its pressure, its molar mass, and its temperature. The higher the molar mass and pressure, the more dense the gas. The higher the temperature, the less dense the gas. Although gases form homogeneous mixtures regardless of their identities, a less dense gas will lie more above a more dense gas in the absence of mixing. For example, carbon dioxide has a higher molar mass than nitrogen or oxygen and is therefore more dense than air. When carbon dioxide is released from a carbon dioxide fire extinguisher, it blankets the fire, preventing oxygen from reaching the combustible material. The fact that the hotter gas is less dense than the cooler gas explains why hot air rises. The difference between the densities of hot and cold air are responsible for the lift of hot air balloons. It's also responsible for many phenomena in weather, such as formation of large thunderclouds during thunderstorms. Figure 10.14, Carbon dioxide fire extinguisher. The carbon dioxide gas from a fire extinguisher is denser than air. The carbon dioxide cools significantly as it emerges from the tank. Water vapor in the air is condensed by the cool carbon dioxide gas and forms a white fog accompanying the colorless carbon dioxide. Equation 10.10 can be arranged to solve for the molar mass of a gas. Molar mass is equal to the density times RT over P. Thus, we can use experimentally measured density of a gas to determine the molar mass of gas molecules, as shown in sample exercise 10.8. Volumes of gases in chemical reactions. We're often concerned with knowing the identity of a gas involved as a reactant or product in a chemical reaction, as well as its quantity. Thus, it's useful to be able to calculate the volumes of gases consumed or products in reactions. Such calculations are based on the use of the mole concept together with balanced chemical equations. We've seen that the coefficients in balanced chemical equations tell us the relative amounts in moles of reactants and products in a reaction. The ideal gas equation relates the number of moles to gas to P, V, and T.